Okay, students, can see the slide?
Yes.
Yeah. Okay, guys, before we start, so tomorrow you'll be going to college, right? We will be having practical in the college, right? Um, all of you scheduled at 10 o'clock, right? According to your timetable. Anyone have scheduled at 8 o'clock? Gavin? Gavin is here.
Need to check.
Oh, I haven't checked. Marwan, tomorrow, what time is your schedule? Do they give any schedule to you? No.
Yes, wait.
11 to 1.
11 to 1. Your practical, eh? Okay then. Okay, so let's be continue. Okay, so we're going to continue with the quantum. So please recall back what you learned last class. So let me go through it first. Okay, so we're still done with the first two topics. We strengthen discussing the first two topics. So talk about photon, a packet of energy of electromagnetic radiation. Then we talk about photoelectric effect, the emission of electron from a metal surface when an EM radiation is exposed. Then we found few problems with outcome against wave theory. It was instantaneous, but wave predicted should have a delay. Then they said existence of threshold frequency. Work wave predicted that should not have any threshold frequency. Any frequency should release the electron. Third, the release of electron is independent of intensity. Wave state should depend to intensity. Okay, then Einstein explained HF, work function, kinetic energy. Then Millikan did that experiment to prove that Vs versus frequency, they found a straight line proving Einstein's idea is correct. Okay. Okay, now we do questions about this one before we go to the next one. Okay. Okay, the first one. So we're going to use Einstein's idea. Look the question, look the solution. So what is the maximum kinetic energy of photoelectron ejected from the magnesium when it's irradiated by an ultraviolet light of 1.5 times 10 to the power of 15 hertz? Work function is this. So means what? The light shines as a frequency of 1.5 times 10 to the power of 15 hertz. Okay. The work function, the bonding is found to be 5.9 times 10 to the power negative 19. The question is, what is the maximum kinetic energy? So, work function, what is that? HF equals to work function plus EK. They're asking what is EK. So, you know, photon energy, work function, you can find EK. So, photon energy, HF. So, just find HF. So, frequency, then minus with the work function, you get the kinetic energy. So, this is the kinetic energy of the electron. Okay. I forgot to tell you something. EK max. Okay. Why they use the word max? Why maximum kinetic energy? Okay, a few questions also asked about why EK max? Why just not EK? Why EK max? Anybody have any idea? Why the Millikan, the EVS, when you calculate EVS is the kinetic energy. The kinetic energy is measured is the EK max, the electron. Why max? Okay. Because the reasoning is if you checked the notes, the EK max, why EK max? Because electron at the surface there is sometimes electron at the inner shell will be released. Okay, not only electron at the surface will be released. Sometimes electron in the inner shell, quite deep inside the metal, will be released. So the electron which in the inner shell, when it released, some energy is required to come to the surface. So that electron will have a less kinetic energy than the electron at the surface. So that means the electron which is coming out, let's say 1 million electron comes out from the metal, not all the 1 million electron will have the same kinetic energy, because some electron is come out from the inner shell. Okay, so the one electron comes out from the inner shell will have less kinetic energy because some energy is needed to come to the surface. But all the electron getting the same packet, same photon. So Millikan only able to get the kinetic energy of the the electron which has the greatest kinetic energy. Okay, because the greatest kinetic energy electron, when it stopped, for the first time the photocurrent becomes zero. So that's why Millikan only can able to find the maximum kinetic energy among the electrons who's moving forward. Okay, that's why they put EK max. In exam, if they ask why EK max, you have to say that the initial electron, when released, some energy is required to come to the surface. So the electron will have less kinetic energy compared to the electron emitted from the surface. Okay, so they will have a range of kinetic energy. Okay, the EVS, that's why we call it EK max. EK max. The electron, the kinetic energy measured is the kinetic energy of the maximum. Any questions? Okay. Next. To use Einstein idea, HF equals to work function plus EK. So conductor has a threshold frequency of 0.85 micrometer. Now this is threshold wavelength. Threshold wavelength. Threshold wavelength linked to threshold frequency. Threshold frequency is C over lambda naught. Speed of light divided by the threshold wavelength is threshold frequency. Okay, first question, find the threshold frequency. So C over lambda naught. Its work function in electron volt. Work function, what formula? Work function is HF naught. HF naught is a work function. The minimum, F naught. The threshold frequency times H is your work function indirectly. So just HF naught, you get answer in joule. Joule you convert to EV. How do you convert joule to EV? Divided by 1.6 times 10 power of negative 19. Okay. See, the maximum speed of the photoelectron emitted when the conductor is irradiated by the blue light. What is the maximum speed of the photoelectron emitted? The conductor is irradiated by blue light. This. So this is HF lah. So use Hc over lambda to find the photon energy is equals to work function plus Ek. So Hc over lambda, Hc lambda use 0.49 micrometer, change to meter. Work function, we just got work function never change. The same metal will always have the same work function. Put it in joule, put it in joule. Okay, when you use this formula, put it in joule. Then you can find Ek. After you get Ek you keep it half mv squared. So find the speed. Mass must be mass of the electron. So I hope this is the idea must be in your mind. Okay, so this is the working. So F naught is 3.53 times 10 power 14 C over lambda naught. Work function is HF naught. This is the bonding. So 1 EV is this much. So we divide by elementary charge. We got the energy in terms of EV. Then we use HF equals to work function plus half EV. You find the Vmax. Any questions from here? So I hope you understand the flow. So remember, HF work function plus EK max, HF we can write written as HC over lambda. Work function we can write HF naught. EK max we can write as a EVS. Okay, stopping potential. Another formula. Okay. Okay, give you 1 minute. Look at the question. Predict the working. Okay, you got idea what to do? Formula is again HF equals to work function plus EK, EK max. What do you want? Calculate the work function and the work function. So how do you get that work function? Work function is two ways. Like if you know threshold frequency, you can find work function already. But here looks like they never give threshold frequency. So work function is HF minus EK max. No? So HF is what? F is 700 nanometer. So C over lambda, C over 700 nanometer, nanometer change to meter, 700 times 10 power negative 9 minus EK max. EK max is, we know, EVS, E times stopping potential. But here, because the cathode is negative 1.5, don't put here negative 1.5, put just 1.5. That's the voltage value only, the magnitude. You put negative, it's going to be plus, then it's going to be wrong. It's just put magnitude only, stopping potential. Then you get the answer. So this is the flow. So, yep. So this is the flow, right? HF work function, EK max. So find the work function, HCO lambda minus EVS. EVS stopping potential, just put 1.5. Any question from here? Okay, so I think it's a straightforward. Okay, this is quite a complex one. Okay, I give you 2 minutes. Guys, look at the question. Look at the graph. Okay, figure out how the answer is going to be. I give you 2 minutes for you to have some idea in your mind. Okay. So hope you have an idea for the first few. Part A, which aspect of the graph could not explain with the wave model? Which feature of the graph cannot be explained by the wave model? Anybody? Okay, anyone? Yeah.
Frequency and kinetic energy.
Frequency. Yeah. What you can talk about kinetic energy?
In wave model, the amplitude is the energy of the light.
Yeah. They found that kinetic energy is found to be proportional to the
Amplitude.
frequency.
Oh.
So that's one factor. The graph shows that the kinetic energy is dependent to frequency. One factor. Or you can say the x-intercept, the existence of threshold frequency. The existence of threshold frequency. It's against the wave theory. Okay. So that's the first one. The wave model of light could not explain why the maximum kinetic energy of the photoelectron depends on light frequency. They also could not explain why there should have a minimum threshold frequency below which no photoelectron is emitted. Okay. So that's the part A. Okay, part B. State the threshold frequency and hence otherwise determine the work function of the metal A. So what is the threshold frequency? This is your threshold frequency, right? The x-intercept. So 1.5 times what? 10 to the power of 15 hertz. This is your threshold frequency. So from here you can work out the work function. Work function is HF naught. Okay. That's working. F naught is 1.5 10 to the power 15. Work function is HF naught. This H Planck constant, F naught. You get that work function. Okay, see, use the graph to calculate the value of Planck constant. Gradient of the graph represents what? Anybody?
Planck constant over elementary charge.
Planck constant of elementary charge. Okay, you have to be careful here. Because the axis is kinetic energy versus frequency. So we go back to the Einstein formula. HF equals to work function plus EK. The graph was EK versus what? EK versus frequency. So rearrange back. EK equals to HF minus work function, right? So Y equals to mx plus C. So your Y is EK. Your gradient will be what? Your X is your F. So your gradient will be what? H. So for this graph, gradient cannot be H over E. It will have to be what? It have to be H. Gradient is H, only Planck constant. Because they use EK max. The previous graph, when our explanation was just stopping potential. Stopping potential versus frequency, the gradient is H over E. I tell you, the type of graph they plot in quantum physics, the y-axis always varies. Can be stopping potential, can be EK, sometimes can be 1 over wavelength. Okay, 1 over wavelength. So you have to use your linear law to predict what going to determines the kinetic energy. Okay, so use this formula, rearrange back, check what is your y, what is your x. The one, whatever beside the x is your gradient. So in this case, Planck constant. Okay, so C is what? The photoelectric equation Kmax, HF. So H is the gradient. So you get the two coordinates, you got the Planck constant. Any questions from here? No questions, eh? So gradient not always H over E. Check your y-axis, x-axis represents what quantity. Okay, next. D. What is the stopping potential when ultraviolet light of frequency 3 times 10 power 15 hertz radiates on the metal plate? So what is the stopping potential? How are you going to find this? From the graph. So you go to 3. At 3, what do you do? At 3, go up, check what is the kinetic energy. The kinetic energy is whatever times 10 power negative 19 joule. So let's say it's 9. So 9 times 10 power negative 19 joule should be equal to EVS, right? Stopping potential times charge. So you can find the stopping potential. So this is the method. For any frequency, you can find the kinetic energy. That's the D. Okay, it's 10. Sorry, you cut properly. Kmax equals to EVS. Get the EVS. Make sure you Kmax in joule. Any questions? Part D? Okay. Part E, last part. Using the same axis above, sketch a line to represent the variation of maximum kinetic energy with frequency F for a metal with larger work function. Okay, so larger work function, the graph going to shift to the right or left? Anybody? Larger work function means threshold frequency going to be large or small? Going to be large, right? So the graph going to shift to the right. Okay, so you get a new threshold frequency. New. So graph shift to the right, the work function is big. Okay, this is a very good question, explaining almost everything about the photoelectric effect. Any part you don't understand here? Okay, so I believe so all of you can cope up what's going on. Okay. Okay, so that's about photoelectric effect. That's about photoelectric effect. So now we go to the next part, next subtopic. Okay. The next subtopic is what's the world now? What is the problem faced by world now? Is it light or a EM radiation? EM radiation, we know it's wave, but now it shows a particle nature only in photoelectric effect. So how to solve this problem? Do light as a particle? It looks like it has a particle nature for photoelectron, but we know it's wave. It's actually wave. So the problem is solved by de Broglie. De Broglie said, introduced a new idea called wave particle duality. Okay, for the first time, this is all a really a stunning development. Like linking two different worlds together. Okay, wave particle. Like for example, electron is a particle or wave. Electron is particle. A particle normally cannot link to wave, right? Wave means should have wavelength. So de Broglie said, why the light we know it's a wave, it has a particle nature. But de Broglie said particle also has a wave nature. Particle also has a wave nature. So what is the proof for that? Particle has a wave nature. You see, Is it electron diffraction pattern? Electron diffraction pattern is a proof that particle has a wave nature. They send an electron in a cathode ray. They send an electron. They accelerated an electron pass through a small carbon film. Carbon film is actually carbon film atom is made of like what? It's made of like a few atoms, carbon atoms. The gap, right? The spacing, the spacing is found to be found to be same size of the wavelength of the electron. Maybe you get confused why I'm saying electron as a wavelength. That's a new concept. I will going to explain that later. The electron, the wavelength of the electron. So when the electron pass through, what happened? The electron, let's say an electron move through a small gap. It's a particle. What should be expected on the screen? The electron pass through a small gap. Electron supposed to hit the center region, Okay. So you should able to see a bright spot at the center. If it's a particle, electron is a particle. But what has been observed here is they saw a fringe. They saw a fringe pattern. Fringe. The electron only hit at the bright spots. Electron only hit at the bright spots. There is a region where the electron doesn't hit. So this is called diffraction pattern. So diffraction pattern. The electron, which is a particle, show diffraction pattern. Diffraction is a property possessed by who? Diffraction is a property possessed by a wave, right? So this is the experiment proving that particle has a wave nature. So de Broglie make a conclusion. He said wave has a particle nature. Proof is photoelectric effect. Photoelectric effect prove that wave has a particle nature. Particle has a wave nature. Proof is electron diffraction pattern. So for the first time in science world, a controversial equation has been introduced by de Broglie. Introduce lambda equals to h over p. It's a very controversial equation. Okay, why is controversial? Very controversial for our understanding. You see, first time you connect two different uh, you connect wave and particle. You see, left side is what? Wavelength. The right side is what? H over p. H is Planck constant. P is momentum. Momentum. Who possess momentum? Particle or wave?
Particle.
Particle. For the first time, de Broglie said a particle as a wavelength. Okay, let's say you have an electron or electron which has a certain mass, certain velocity. Let's say it possesses certain momentum. How much is the wavelength possessed by this electron? Lambda equals to h over p. Put the momentum value, you get the wavelength. So that's the wavelength of the electron. This also can be applied to you. You yourself, when you are walking, you have your momentum. Okay. So according to this idea, they say the human, you as a particle, will possess a wavelength. Tell me, the wavelength possessed by the human compared to electron. The wavelength possessed by the human compared to electron will be very small or very big.
Small.
The wavelength going to be very, very small because momentum is huge. Okay, very small wavelength. Can it show diffraction pattern?
No.
Can't show diffraction pattern. Okay, so this formula only works so far for a subatomic particle, especially electron. Okay, so yes, so we come to the equation. The photoelectric effect is a particular nature. moving particle interference diffraction pattern, which are wave property. So de Broglie introduced lambda equals HOP. The lambda is called a special name called de Broglie wavelength. And we call it what? We call it de Broglie wavelength. Okay. So lambda equals to HOP. The P is MV. Okay. Einstein theory, you don't need to know. Relativity, you don't need to go for the relativity. Just lambda equals HOP now. Okay. So what is de Broglie wavelength? In an exam, they ask what is de Broglie wavelength? A type of wavelength associated to a electron, a particle which possess momentum of p. Okay. De Broglie wavelength is a wavelength associated to a particle which possess a momentum of p. It's called de Broglie wavelength. Okay. Bigger the momentum, smaller the wavelength. Smaller the wavelength, it can't show its wave nature easily. Only small particle with small momentum can show the wave nature. So this only works for electron so far. Okay, so this is called what? Wave particle duality. Okay. So electron diffraction pattern is proven. Particle exhibits wave property. Okay, now question has been asked about this electron diffraction pattern. Okay, they ask the speed of electron, the electron moving forward is increased. Speed of electron is increased. How the pattern going to change? Is it the fringe going to get closer or the fringe going to get further? So what's the answer? And the speed of electron increased. How the fringe pattern going to change? It's going to spread further or is it going to get closer? So how to know? How to know? Check the wavelength. Yeah, greater?
Wait, V increases, lambda will decrease.
When speed increases, momentum of the particle increases, so lambda will decrease. When lambda decrease, you're going to diffract more or diffract less? Less diffraction or more diffraction? Big wavelength diffract more or small wavelength diffract more?
Big.
Big wavelength diffract more, right?
Yes.
So here wavelength suddenly becomes small. So what happened to the diffraction? Become less significant, right?
Yes.
Less significant means what? The fringe get closer or further?
Closer.
Fringe will get closer. The fringe will get closer, very close. Okay. If the speed increase further, the wavelength become very small until become what you're going to see here, just a dot, just got a dot. The fringe all will get closer, just a dot. You can't show the diffraction. Okay. So in exam they do ask this. And speed of electron is increased. What happened to the diffraction pattern? So I've said the diffraction and speed increases, momentum increases, de Broglie wavelength becomes small. So the electron less diffracted, so the fringe get closer. Okay. Okay, so let's move on now from here. Okay, so temporarily, the idea of the problem faced by the world about photoelectric effect has been solved by giving an idea of wave particle duality. de Broglie is lucky because we have a proof to show that particle as a wave, which is the electron diffraction pattern. If people can't see electron is diffracted, I don't think so. His idea will be recognized. Okay. If I'm not mistaken, de Broglie got Nobel Prize, but this is if I'm not mistaken, is PhD thesis or a master's thesis. PhD thesis, I think. He revealed this, and his thesis gave him a Nobel Prize. Okay. Okay. So now we're going to bring this idea to the questions. So when an electron pass through the two slits, they say you're going to hit only at a specific points. Show diffraction pattern. Okay, so like for example, you let's say you have a two opening. You have a two opening. Okay, two slits. You throw a tennis ball, fire a tennis ball, lots of tennis ball. Okay, according to wave particle theory, the tennis ball should only hit at a specific points. Show diffraction pattern. But when they do that experiment, they couldn't see that. They couldn't see the diffraction pattern. Why? Because lambda equals to HOP. The momentum of tennis ball is still huge, so the wavelength is quite small. Cannot show the diffraction pattern. Okay. But this is what predicted. They said every particle has wave nature. Okay. But how strong is the wave nature depend to how big is the momentum it possesses. Like you, when you run walking, you get a certain wavelength. When you running, wavelength get smaller. But you walking or whatever, you can't show the wave property because the wavelength is too small. That's the idea brought by quantum world. Human as a wavelength. Sounds funny, but you cannot neglect it. It looks proving something. Okay, because de Broglie proof, electron diffraction proves that, and photoelectric effect proves that. Okay, wave particle duality. Okay, so now if you see these questions in your early studies, you will say something's wrong with the question, right? See now the questions. Calculate the de Broglie wavelength for 10-gram bullet traveling with a speed of 300 meters per second. So it's a bullet like a particle. What is the wavelength it possesses? So now lambda equals to HOP. H divided by the momentum of the bullet. Momentum of the bullet is what? 10 gram change to kilogram times the speed. So we get the wavelength. Okay. And so on. All going to be find de Broglie wavelength. Electron, proton moving with this potential. Second, electron traveling with the speed. So lambda equals to HOP. Mass of the electron times the speed of the electron. Get the lambda. The mass of the electron is given. Third one, a proton accelerated through a potential difference of 100 volt. How do you find momentum for this? C. Anybody? A proton accelerated through a potential difference of 100 volt. Find the lambda. So EV equals to kinetic energy, right?
Yes.
EV equals to kinetic energy. Okay, I tell you, when come to de Broglie wavelength, you need to know momentum. Momentum. So half mv squared momentum, we know is mv. mv. Yeah. So to find momentum, your kinetic energy, don't write half mv squared. I think there is another better form. P squared over 2m. Kinetic energy can be written as P squared over 2m. Where P is momentum, this is mass. So you can find the P straight away. But how P squared over 2m? See, half mv squared is the kinetic energy. You times both sides with m. Times both sides with m. What happened? It's going to be half mv squared. So EKM. So mv is P squared, P squared over 2 EKM. So EK is P squared over 2m. P squared. So kinetic energy can be written as P squared over 2m. It's very convenient because we straight away can find the momentum, then straight away we can find the wavelength. Okay. So yes, so that's the working here. Okay. Last one is slightly different. Half mv squared, find the momentum, then put the momentum inside, then you get the answer. Any questions, guys? This first question. De Broglie wavelength. Okay. Now let's proceed. Okay, so that's about de Broglie wavelength. Okay, just its introduction. Okay. Okay. So now, next, the quantum physics doesn't stop there. Okay. People still have confusion, although it solves the problem explaining photoelectric effect, and the de Broglie give out a controversial link between wave and particle. Okay. People still not really have confidence on quantum physics. But later, quantum physics contribute something very important to the world. Another important stuff. What is that? It involved in atomic structure. It able to explain the atomic structure. Okay, atomic structure. You learned last time. Which are the scientists contribute to the atomic structure? The first who? First is Dalton, right? Dalton, Thomson, and after Thomson, J.J. Thomson is Rutherford, the famous one. Rutherford. After Rutherford is who? Anybody?
Wait.
First J.J. Thomson. J.J. Thomson said the plum pudding model. Then Rutherford did the alpha part, what do you call? Alpha scattering experiment, bombarded to a gold foil. It's a big breakthrough about atomic structure. After Rutherford, which scientists contribute to develop the atomic structure further?
Wait, is it before John Dalton?
After Rutherford. Niels Bohr.
Oh, yeah.
Niels Bohr. Niels Bohr.
Oh, yeah.
What is the contribution of Niels Bohr?
Neutron?
Actually, Niels Bohr, Chadwick. After Niels Bohr, Chadwick discovered neutron. Niels Bohr discovered Niels Bohr discovered what? Niels Bohr discovered that the electron has specific energy levels.
Oh,
The electron has, the electron has specific energy levels. That's the discovery of Niels Bohr. You see, electron cannot stay any energy level it like. You only can stay at a specific energy levels. Okay. So Niels Bohr's contribution. Okay. How Niels Bohr get these energy levels? Niels Bohr get these energy levels by using quantum physics. By using quantum physics derivation. You got these energy levels. Okay, now first, before we go to Niels Bohr, Rutherford model got one big problem. Okay. What big problem is the drawback? The drawback of Rutherford model. What Rutherford said? Nucleus at the center, surrounded by electron, right? Electron go around. So Rutherford got one big problem. The problem is, according to Maxwell, anyone heard of Maxwell? Maxwell is another scientist. I think he died very young. Okay. But if he survived, I think he died around 40 years old. I think less than 40, I think, if I'm not mistaken. But if he stayed until 70 years old, I think his idea going to be like going to on par with Einstein. Okay, very genius guy, very low profile, but he's the pioneer of development of radio wave. Okay, radio wave. So according to Maxwell says that if any charged particle accelerates, right? According to Maxwell, any charged particle, if it accelerates, it give out radiation. It give out radiation. Okay, it has been proven because its idea has been used later to develop radio wave. Radio wave. So So he said, if any charged particle accelerates, give out radiation. Its energy, the particle energy will convert it partially to EM radiation. So when the charged particle accelerate, give out EM radiation, what happened? The charged particle become less energetic because loses energy, because some energy convert to EM radiation already. So then what happened to the particle? It become less energetic. Okay. So that's the idea given by Maxwell. Okay. So according to Rutherford, you see, according to the classical electromagnetic theory, a charged particle were accelerated around another charged particle, then with continuously radiation of energy will happen. Energy will be radiated. That's EM radiation. So the loss of energy would slow down the speed of electron. Yeah, the electron is going around in the nucleus. The electron is accelerating, right? Electron moving around the nucleus, accelerating or not? Where is it accelerating? Towards the center of the nucleus, right? Yeah, circular motion. Circulating one. Because the electron is accelerating toward the center, so it gives out radiation. So electron should lose energy. If when it loses energy, what happened? Electron would fall into the nucleus. The electron get slowed down means it's going to fall, get closer to the nucleus until fall to the nucleus. Then the electron should not exist anymore. Only nucleus should be there. But such a collapse does not occur. You can't see the electron is collapsing to the nucleus. So Rutherford model unable to explain this fact. So there is a drawback in Rutherford model. Okay. So what is the drawback? The electron, a charged particle which is accelerating, give out EM radiation. So you should lose energy and should fall to the nucleus. But doesn't happen. That means its nucleus idea is okay, no problem. But its electron, there is some improvement need to be done. So later, Niels Bohr. Okay. Niels Bohr solved the problem. He said by using a quantum theory. It's I think it's a few pages of derivation, not in your A-level syllabus. Use a quantum theory. Use the de Broglie formula also. Lambda equals to HOP has been used. Okay. Lambda equals to HOP formula is used. And the energy levels of the electron has been developed. And Niels Bohr said, according to Niels Bohr, the important idea, the electron travels in a stationary orbit, stationary wave. The electron is found to be only possible at certain energy levels from the quantum theoretical. So electron cannot stay at any energy levels it likes. It has only a certain energy level. Okay. And he said, he postulated that the emission of light occurs when the electron move into a lower energy levels. Okay. He said the electron will be going around in every energy levels. If the electron receive energy from outside, maybe light, okay, receive energy from the light, the electron suddenly will jump to the next energy level, go to the high energy level. Okay. When the electron wait for a while, when the surrounding is very cold, the electron suddenly will drop to a low energy level, releases the energy. This is the idea, you see. Okay. The main contribution Niels Bohr is electron as specific energy level. Okay. So yeah. Later is Bohr idea. So say the electron got lots of energy levels. It got lots of energy level. The energy level will get closer and closer. Okay. So this is the introduction for this Bohr idea, because time's up. So the next class we will go in depth about this. Okay, you can read this. You can check my videos, the seniors one. Okay, you can get understanding. So quantum later, Niels Bohr uses quantum idea to get the atomic structure for the electron, and later it was proven. This is the proof for Niels Bohr that there is energy level exists, and Niels Bohr got Nobel Prize explaining the electron energy level. Okay, then the quantum idea become more firmed up. People start to believe quantum is something very important, which explaining some stuff which is unable to explain by classical physics. Okay, guys, any questions? So this is the introduction. We never go in depth about the atomic structure yet. Okay, just introduction that quantum contributed to the atomic structure. Who contributed this? Niels Bohr. Niels Bohr used quantum physics to explain electron as energy levels. Okay. So any questions? So what did you learn today? So you learned about de Broglie, Paeflen, wave particle duality, then atomic structure. Okay. Okay, so I stop here. So see you tomorrow. Tomorrow your lab is 11 to 1.
Okay.
11 to 1. Anyone shifted to any other lab? Nobody, Nobody. Marwan, you also 11 to 1.
11 to, yeah.
11 to 1. Same as your timetable practical schedule. Okay then. So guys, so see you tomorrow. So bring a graph paper. Bring a graph paper with you. Okay, I already submit the Word file. We're going to do the first experiment, capacitor. Okay? Stop. So see you then. Thanks.